TTL Computer 2. Today, we're going to take a break from our PCB design to revisit our digital simulation and our control circuit. So it came to my attention a few weeks ago. A video popped up in my YouTube feed, and it was regarding pitfalls of using EEPROMs for combinatorial logic implementations. And that's obviously what we are doing and utilizing for my TTL computer. We're using EEPROM to implement our control logic. So that made me aware of this issue, and we're going to take a look at that today and my selected solution. So our pitfalls or issues really are coming from two sources. And I said the first one is the use of EEPROMs for combinatorial logic. But also this highlights a second pitfall, if you will, and that's within the digital simulation itself. The digital simulation does a great job, a fantastic job even, being able to, to mimic and realize the digital solutions, in software. But it's not, it's a simulation, and it's not a perfect simulation, such that we'll look at the issues we're having with the EEPROMs in a moment. But this issue and one similar to it are not surfaced in the digital simulation. So the digital simulation that's one of the pitfalls, is that it's an imperfect simulation. And the second pitfall is that it can kind of lull us into a false sense of security, that something that looks good in the digital simulation, once we actually realize that in physical hardware, we might have problems yet because the simulation didn't account for certain issues. But all right, let's go on. Okay, so what we're looking at here is from the EEPROM data sheet that we're using for the 8K EEPROMs, and we're looking at the signal timings. Now, I in fact, read through this data sheet quite some time ago, maybe even before we started TTL Computer 2, and I kind of was aware of this one point that we'll get to in a minute, but I think it didn't really make as important impression on me when I read it as it should have. And I also fell into that digital simulation, pitfall, being overly confident that the simulation was working good, and that we weren't going to have issues down the road. But anyway, so let's look at this in a little bit more detail. So we're looking up here at the signals up here, and these are the signals that are driving, right, the address to the EEPROM. We provide a 16-bit address to the EEPROM, and then it outputs 8 bits of data at the output pins. So this is showing here that we have the address signals going up and down. The bits are going on and off to construct the address. And then here is kind of signifying at this point the address lines, signal lines have stabilized, and now the address is valid. Now this is the key thing. So down here we look at the output signal from the output byte from the EEPROM. So we can see here this line starts the point where the address input to the EEPROM has stabilized. Now we have this time period all the way from when the address is stabilized to when the output is stabilized, okay? And that's this TACC time. And we can see here, looking at the output, that the outputs, the address changes, the control circuitry of the EEPROM has to react to that. It starts to affect the output changes, here, and then the outputs are not stabilized to here. So when the outputs are beginning to change state for the EEPROM, the output data bits this is an undefined state, and by undefined, that means the chip does not guarantee, the EEPROM does not guarantee that a bit that's supposed to be high is going to be high and a bit that's supposed to be low is going to be low. It's undefined, and they could be bouncing up and down in an erratic fashion until this time period is hit. And this time period is 150 nanoseconds, and that's relatively a long time. So as a comparison, a typical logic gate, the propagation delay or this time for the typical gate is from 8 to 15 nanoseconds. So this time period for the EEPROM is 10 times or more the delay time as a normal logic chip. And to fully, when our clock signal from my TTL computer, which is running at 4 megahertz with a 4-phase clock, our individual clock signals are 250 nanoseconds. So the NOT clock is active for 250 nanoseconds. So this time period for the EEPROM of being basically undefined is over half of the period of our clock signals. This is a problem. And so besides this time delay being a problem, that's one phase of the problem. The second phase of that problem is that these bits, we cannot count on the level of these signals of being high or low. It can be noise, it can be gibberish. And if these bits, are connected to our control lines that are let's say providing the tick counter reset, that's a really big problem, because if the tick counter reset signal goes high, that's effectively shortcutting the currently executing instruction and beginning the next instruction. So that's a really bad situation. So again, so those are the two issues: the length of time, 150 nanoseconds before the EEPROM data is valid, and the other one is that the signals could be going up and down before that time. Okay, so now that we know that if the address changes, we have to wait 150 nanoseconds before we can use the output. And we have a few things that are driving the address signals, right? We have the tick counter or the step counter is one of the inputs to the address. We have the instruction register output, or the instruction that we're executing is part of the address. And also our 3 flags are providing the remaining bits for our address. So if any of these items change, we have to wait that 150 nanoseconds before the output is valid. And we have one other source of change for the address, and that's the microcode tick reset signal, right? That ends the currently executing instruction by resetting the tick counter, right? And that's obviously resetting, part of the address back to 0. So again, we have that 150 nanosecond delay. So I think you can start to see that those are two significant issues that we have not addressed at all in our current simulation. The current simulation assumes that the outputs from the EEPROM are going to be valid after one normal propagation delay, and it's not. It's 10 propagation delays. Okay, so what's our remedy look like? Our remedy is that we are going to implement a latch on our control signals so that we can clock those in at a specific time, and that they will be held constant and consistent until our next control latch in cycle. We're also going to need to resequence our clock signals, the NOT clock, P clock, U clock, and T clock. We'll see what those are, how we're going to do that in a minute. And we're also going to have microcode changes, and we'll look at all these three things in the next few slides. Okay, so these are our control signals, right? Not clock, P clock, U clock, and T clock. We said we have a four-phase clock signal, right? And we do we do specific things on specific ticks, on ticks of the clock. And I'm not going to go over that again, but this is what we're going to need to do on the new sequence. So we see that we have on our not clock updates the tick counter, and it also enables the control signal output, right? This essentially starts the timer for our 150 nanosecond delay. Now we're going to have a control latch that's going to latch the outputs from the EPROMs in a known state, so they stay consistent for as long as we need them to be consistent. And we're going to do that on the P clock cycle. So what we're really doing here is we're taking these signals, the P clock, the U clock, and the T clock, and we're shifting them forward, right? What we were doing on the P clock, we're going to now do on the U clock. What we were doing on the U clock, we're going to shift that down. Now we're going to do that on the T clock. Sorry about that. Now we're going to do that on the T clock. And since we shifted those down, right, it freed up the P clock for us. And we are going to use that P clock signal as our control signal, our latching signal. So we're going to push down the T clock to the where. We don't have any more clocks. We have a four-phase clock. So this is another problem, right? So what are we going to do here? So what we're going to do is we're going to leave this on the T clock. So instead of just these items being updated on the T clock, or we're also going to do what we were doing on the T clock by itself before, the memory address register and the program counter updates. We're going to do them together. But this is the implication of that. Since we're doing these together, if we ever have a microcode step that needs to do this and this in the same tick, we need to split those into two ticks. In other words, we'll have one microcode step do this, and we're going to add an additional microcode step to do these. So they're both gonna occur on the T clock phase, but they're not going to occur in the same microcode step. So this was our first area that could potentially have been a problem, because we need to now go through all of our microcode and add the extra step for these cases where we had microcode steps doing these at the same time. Fortunately, there's not that many of them, and really fortunately that we did not have, this condition did not exist in any cases where we didn't have an additional free microcode step to introduce the extra step. We almost didn't have enough to do our call statement, but we just had enough microcode ticks left. Remember, we have 16 microcode ticks. Since we have a 16-bit, the tick counter is 16 bits. We had just enough to do the call statement by adjusting the microcode. So that was our first part of the changes. We shifted everything down in our clock phases. We reused the P clock for our control latch, and we had to update our microcode into two instruction microcode steps if they were one. Okay, so now let's take a look at our control signals and how they're going to be used now. And I hope you can follow through here on this, but we're basically looking at our control signals over time, and we have this our not clear signal, which is a reset signal. So this reset signal goes low, which means we're in a reset condition. If either the not clear signal is low or the tick reset has been raised in the microcode and we're in the not clock step. So both of these conditions, either the not clear signal or the tick reset in the not clock phase are both reset signals, right? So let's kind of go through, assume we're in like a power on situation for the computer. As part of powering on, the clear signal is going to be held low for a given period of time for the whole computer to start up. So the clear signal is going to come low, and when we're in the clear state, that resets the tick counter, and it resets our program counter as well. And when we reset the program counter, right, we go to the not clock phase, right? The not clock phase is brought high, okay? And when this is our control latch, and the control latch is going to go low if we are in a reset state, right, which is here. So the control latch is going to go low, and this is high Z. So that means the output from our EEPROM latch is going to go high Z, and the control signals are just going to float to their default state, which is just everything is turned off. There's no output from the registers. There's no input to registers. Everything is disabled. So this is like our safe state. So also this begins, right, the address bits are all changed here. The tick counter is brought low, everything is 0. And this starts our 150 nanoseconds here. And so now that's started. The reset signal is released, which means the computer can start to run. So now the not clock timing starts here, right? The not clock is now starting its first 250 nanoseconds, and the not clock is ending, and the P clock is beginning, right? Not clock, P clock, U clock, T clock, not clock, P clock. So not clock ends, and the P clock is beginning. And when the not clock ends, the control latch now goes active. So right at this phase, the P clock is going high, the control latch output is enabled, and right here is where we are signaling, we are capturing the output from the EEPROM, and we are clocking that in to our latches right here at the the transition of the P clock to the high state. Now, that 150 nanoseconds, ended about here someplace. So the EEPROM output has stabilized here, before the not clock is finished. So that's the outputs are all good. Again, the P clock goes high, and that latches in the outputs from the EEPROMs. Now the P clock is ending and the U clock phase is starting. Here, the flags in the instruction register are going to be changes, if there's any, will be clocked in. This is going to again affect the EEPROM and start that 150 nanosecond delay. But we don't care about that because our control latch is locked high. So the EEPROM here is changing. It's going in that invalid state where we have the delay, and then it's going back high again. The outputs from the EEPROM are high. But again, we're relying on the outputs from our latch, and that hasn't changed. That's still good. Okay, so the U clock ends, the T clock goes. Maybe we did some updates on the memory address register and the program counter. These will change. Again, the address inputs to the EEPROM are going to change here. So this again starts that 150 nanoseconds delay, but that will end about that. The outputs will become stable again from the EEPROM about here. But again, we don't care. because we're relying on the output from our control latch. The T clock phase is ending and the not clock phase is beginning again. Not clock is going high. So this is our reset condition again, right? Now, our control latch goes high Z, right? Floats back to the default. The not clock comes up. The tick counter is advanced. The program, the EEPROM address is changed because of that. And again, we have that 150 nanoseconds occurs here before the EEPROM outputs are stabilized, but they're stabilized about here. And then the P clock starts to, right, the not clock is ending, the P clock is beginning, and our control latch again goes, output is enabled with the rising of the P clock, and we clock in the EEPROM, outputs back into our latch, right? And we're back here again, right? We started that again. So that's the solution. And so this is the updated control circuit. So you'll see here that what were our 245s before, I have replaced with D latches, and these D latches are the same latches that we have used to implement our registers. So these are pretty much drop-in replacements for the 245s, and I've added in an extra latch, and this latch is for EEPROM control signals that we are only using in our control board, which is the tick reset signal and instruction register in. Those are not brought out to the wider signals bus on our backplane. They're just used on this PC board. But so you can see here that we have the P clock is driving the clock in of the latch signals for each of our latches, as it should. We have the output enable for our main latch registers, is controlled by the not clock and the clear signal, like it should. That right, if not clear is active or not clock is active, right, these are in high Z. The output goes tri-state and these float. We don't do that with these two signals, however. The tick reset and instruction register in signals, we don't, these are active on the card all the time. So this is always driving these signals. And then, this is new. So this is the logic for our reset signal. And again, this is the reset signal that is either when the not clear signal, which is pretty much our reset signal, if that signal is high, or if the tick reset is raised from the microcode and it's the not clock phase, right? We issue the reset signal to our tick counter. Okay, so those are the changes that we needed to make in our control circuit. Now, so this is our main diagram of our digital simulation. So because we changed, because we essentially pushed our clock signals down forward from not clock, P clock, U clock, and T clock. The signals had to be changed where they were used, right? This was P clock before, needed to be changed to U clock, right? This was P clock before, needed to be changed to U clock. And these were P and U and had to be changed to U clock and T clock. Okay, and program counter and memory address register, these were already on T clock, so they did not have to change. Oh, one other change that I had to make was here. this was our write signal, and this was the write signal that's basically used by all of our devices, the RAM and any of our devices like the hex display device. This was the signal that was used to clock in, the data that was being written to those devices. And I had to change this. So what I was doing here was taking that clock signal and ANDing it with the P clock, and then that was what was being output here. So, I was already doing that. The right signal has to occur in the P clock phase. But now, since these signals are all latched in the not clock, I could not do that anymore. So I had to make this be just the the right enable signal, and any place that we were doing the doing an actual write, again, which would be in the memory circuit, or in any of our devices like the hex display, right? So before, this was just the write signal. Now I have to separate that out. I have to do this is like the write enable signal, and then the U clock is where it needs to be clocked in. So I had to add this extra bit of work for the devices to use as their signal to clock the data in. Okay, so all of those changes have been affected in the simulator, and the microcode has been updated, and we're still able to run. So that's a good confirmation. So that's it in a nutshell. Kind of a lot to digest, but yeah, there were some pretty big oversights that we had, in our control circuit because of the issues that we reviewed. But pretty happy with the way the changes ultimately, what the remedy ultimately looked like. It's a completely deterministic solution, right? It's based on the 4 phases of our 4 clock phases, and there's nothing in there that's dependent on any built-in delay circuits for our timing. And I'm pretty confident. Again, we're going to start out my TTL computer 2 with a 4 megahertz clock, and I'm pretty confident that we can easily go up to a 6 megahertz clock, and we'll be running fine at 6 megahertz. So that's it for today. I think in our next video, we're going to get back to our PCB design and manufacturing, and we're going to jump in next with our registers PCB. And that's going to be a really significant PCB that's going to be interesting to test in our testing jig. But that's it for today. Until next time, thanks for watching.